Yeah, welcome back here in the room and online for our next session on, let's say, sort of a hot topic, carbon dioxide removals. So the moderator of this session, I have the pleasure to welcome Geert Fremout. Geert is Head of Unit International Negotiations and Cooperation at the Belgian Climate Change Department in the Ministry of Health, Food and Environment. He's a colleague of Peter Wittig that opened the forum yesterday. Geert, the floor is yours. Over to you.
Yes, can you hear me?
Not yet. Oh.
Yes, good morning. Morning all. Yes.
No. They can't hear me.
Yours is on.
Yours.
I'm on. Yeah. Okay. Yes. Thank you. So, yeah, I understand that this seminar is like trying to enhance the interface between science and policy. So I'm clearly at the policy side. I'm not a CDR expert, but I'm very much interested in the topic because we also, in the negotiations and in policy making, of course, we start discussing this every time more and more. We already had, how would I say, a smooth start a little bit at the end of the last session into the CDR discussion. And so now we have almost 2 hours to have a more in-depth discussion with two with two presenters who will introduce the topic. Miles Allen is a professor in geosystem science at the University of Oxford, and will start off, and then we will have a presentation from Steve Smith, who is the research director of the Smith School for Enterprise and Environment, also at the University of Oxford. And afterwards, we will then have a panel discussion with Soheil, sorry, and also with John Martin, I believe, who is present here as well. Alexandra Deprez should also join the panel, but she's, I understand, participating in COP16, and we are still trying to locate her. And if she can be us, that would be great, and otherwise we will have to do without. But without more, I would like to give the floor to Professor Miles to give an introductory presentation. I believe this will also make the link to what is the implications of the definition that is used, for example, when we talk about carbon dioxide removal. You have the floor.
Thank you very much, and thank you very much for inviting me. And so Frank encouraged me to give you a presentation on the physics of carbon dioxide removal. So I have some equations in my presentation, but depending on how long you want the presentation to be, you can always sort of stop me if they appear. But I was trying to explain to Frank last night. Philosophically, I feel that we should think about equations more. They're a unifying. They could be a sort of something to unify around. Do I have a clicker, or I do have a clicker? Oh, here we are. Great. Okay. So in the particular point I want to talk about on the sort of definition of CDR is understanding the role of passive carbon uptake, and I'll explain to you what that means in a minute. Do I? Yes. Okay. So if you find this presentation interesting, you can read all about it shortly in a paper to appear on the 18th of November, looking at quantifying the impact with many suspects, including Pierre in this room, and the authors. But you may recognize these are the authors of all the ones we could find, at least, of the 2009 net zero papers. So if you recall, but back in 2009, 6 papers were published in very quick succession, which introduced the need for net zero emissions to halt global warming. And the meaning of net zero has evolved rather since then. And so the main point of this paper, which is appearing shortly, is to explain how the meaning of net zero has evolved and to sort of get back to what we originally meant by net zero, which we're clarifying is geological net zero, because that's what it actually takes to deliver what we said it would deliver. And I certainly, as one of these authors myself, I'm very concerned that we've told policymakers that net zero is the answer without being quite clear what the question was. So I don't know if you know the Hitchhiker's Guide to the Galaxy, where the answer is 42, but then what was the question? And so everybody's very clear that net zero is the answer, but it's become a little unclear what the question is. So crucial, I think this was talked about yesterday, that the crucial definitional ambiguity in net zero is the response of the biosphere and the oceans to past emissions. This has acquired a lot of discussion in terms of the so-called managed land issue. You can see here the biosphere responding to emissions, to higher CO2 concentrations in the atmosphere over the past century, and all that vegetation growing. And we're starting to, I've yet to hear the phrase managed oceans, but it's probably coming. Countries are increasingly talking about monetizing blue carbon in their exclusive economic zones. 30% of the world's oceans are in somebody's exclusive economic zone, and probably more than 30% of the carbon which is taken up by the oceans is taken up in coastal zones. So, just to remind you what we originally meant by net zero back in the 2009 papers, we have the familiar scenario on the right: emissions defined by the IPCC glossary definition, which excludes explicitly that passive response of the carbon cycle to past emissions. So in the IPCC glossary, removals are only consequences of human action that is additional to the response of the natural system to past emissions. And that response is important because you can see there in green, that's the passive uptake that results from our past emissions, which is at the moment, it's very significant. It's 20 billion tons of carbon dioxide per year. It declines as we reduce our emissions, but not all the way to zero. And that, because it doesn't decline all the way to zero, carbon dioxide concentrations after mid-century start to fall. They fall at about 0.3% per year. And that's because that carbon is it's not being destroyed, that CO2 is being taken up by the oceans and biosphere, so it's going somewhere. And that's what it takes to limit warming. So the right-hand panel shows you the warming response. So if we use the definition of net zero as defined in IPCC assessment reports, that's sufficient to halt CO2-induced warming. I've shaded in on the left-hand panel now the component of the passive sink that is taking place on so-called managed land. So that's actually in national greenhouse gas inventories, including the European Union's, that's regarded as a removal. So in fact, if we use the definition of national greenhouse gas inventories, this is what emissions look like. They're lower. Okay, so the black line is smaller, and the green line is also smaller. So we've reallocated emissions from the passive sink to active removals. And so we've reduced our net emissions. But you'll notice the CO2 concentration line and the warming line are the same, because all this is it's just an accounting reallocation. But there's something very important here. Notice, and it's quite small on this plot, so you may escape you, but the black line now goes below zero. Yeah? So do you see how the black line, the new heavy black line, goes below zero in order to stop global warming? It doesn't go very far below zero because we only reallocate some of the passive sink. But as I said at the beginning, there's a lot of enthusiasm among the carbon accountants of this world to find new carbon uptake to monetize, to sell in offset markets, or to include in international transferred mitigation outcomes. under Article 6 of the Paris Agreement, which of course is now operationalized, so it's, countries are now going to start using it. And what happens if, you could make an argument that if any of the passive sink is going to be called a removal, well, it all should. Why should Guyana get benefit for its forest when its neighbors in the Caribbean don't get benefit for the carbon uptake by their coastal oceans? In fact, the neighbors of Guyana, Grenada, I believe, and the Bahamas have noticed this and are busy saying, no, we want to be able to sell carbon uptake in our coastal oceans. So suppose you take to the logical extreme, and I think we can be confident that accountants are very good at this, so they will, if they're allowed to, they will definitely go this way, and reallocate the entire passive sink to negative emissions, to removals. And now you see that the newly defined emission line has to go far below zero in order to halt global warming. But, of course, the CO2 concentration line and the warming line remain the same. So provided we adjust our targets consistently with our definition of emissions, everything is okay. But what if we don't? And this is, of course, the point of this paper. There's a relatively small change in the emission line between the black and the dotted, okay? Where instead of going below zero, we just go to zero, okay? But using the new definition of emissions. So we adopt the new definition of emissions in the greenhouse gas inventories, not the one which was used by the IPCC, but we still aim for net zero in 2050. What happens then? Well, what net zero then means, we've rewound the clock all the way back to 1992, and we're aiming for stabilization of greenhouse gas concentrations. It's not what we meant by net zero anymore. And that now results in a flat line in the center, because the net flow of CO2 into the atmosphere is balanced by net removal. But net uptake, I should be careful about using the word removal. But temperatures continue to rise. And that's, of course, easier to achieve if I show you using the original IPCC definition, which allows you to sort of see what this means for active emissions. You can see that this is with the original IPCC definition of emissions. What that entails is we have to reduce our emissions by 70% or so, 75% perhaps, and then we have like 100 years or so to continue reducing them. We're still allowing ourselves to emit quite a lot, even in the middle of next century. But the world still warms. And there's worse, just in case you find that depressing. Imagine that we actually progressively reclassify the passive sink as a removal, as it's needed, but still fooling ourselves into thinking we're on a path to net zero in 2050. What happens? Well, it's more than 10 years before we actually need to start reducing emissions at all. We can just get by just finding more passive sink to pretend we're reducing our emissions. And we'll find a developing country, we'll do an ITMO, an internationally transferred mitigation outcome, take advantage of some more of their natural passive sink, and then you end up with the dashed line here, which is essentially what you get. Pursuing the rules correctly, this is not cheating, okay? So it's not that, I'm not talking about, many people criticize the offset markets for all the fraud and so on which goes on in them, but no, this is assuming everything is completely correct, done correctly. You can actually avoid actual emission reductions for over 10 years. Then, of course, you need to reduce emissions because you run out of passive sinks, but you end up with warming now well over 2 degrees and keeping on rising in the future. So who would be crazy enough to do this? Well, this happens to be exactly what we're doing. And this sort of shows you in another way, the challenge of it is that, the present day, as the Global Carbon Project tells us, we're putting carbon dioxide into the atmosphere. A lot of that's being taken up by the terrestrial biosphere and ocean in this passive uptake, but almost half of it is ending up in the atmosphere. That's the blue curve. And then there's various things we could do. We could sort of reduce immediately, and that would give us this immediate offset of ongoing emissions by the passive sink, which gets the blue bar to zero. So you could, but of course then immediately your sink would start to decline. So you've got those three possibilities over on the left, over on the right. Stable concentrations, a sort of temporary net zero where you're still balancing some of your remaining fossil fuel use with active removals to the land sector, and finally durable net zero where everything's balanced. And the problem is that if you've got a good enough accountant, all four of those right-hand could be counted as net zero, but only one of them is a durable net zero, and it's also, of course, the most expensive one. When do you want me to shut up?
How much time do we just do?
I'm an academic. 5 minutes. Okay, that's fair. Because the last point we wanted to make in this paper, so what I'll do, I think that's a good result for everybody because it means I'll skate over the equations, but they're provided to everybody if you want to sort of go back and work out what I was talking about. So this passive uptake is essential if net zero is actually going to do what we promised it would do, and halt global warming, and it's under threat. We saw in the Canadian forest fires last year and so on. I mean, the ability of our biosphere to absorb carbon is degrading. And it needs protecting. And countries like Guyana, Bhutan, Suriname, Gabon are sort of clubbing together to say, look, we are providing the world a service with this passive sink. Why are we not getting credit for this? Where other countries, which cut down all their forests and are now replanting them, are getting credit for doing something which is much more environmentally damaging. So we need to protect passive sinks, but the main mechanisms for channeling resources to sink protection, the voluntary carbon markets, Article 6 and so on, they're all based on this false premise that somehow a passive sink is compensation for ongoing fossil fuel use, which it's not. And fortunately, and this is the point we make in the paper, physics does suggest an answer. And so if you'll bear with me, maybe I'll skate directly to, no, why not? Bear with me. So the change in global average temperature over a multi-decade time period, okay, so that's just, the warming we get over a few decades, is proportional to two things. Basically, the change in energy imbalance over that period and the average energy imbalance over that period. So it's very important. There's two components to this. So even if we stabilize concentrations of greenhouse gases, which means the energy imbalance is constant, so delta F would then be zero, we still get warming, okay? Because we have this adjustment to the fact that this is on, it's an approximation, of course, but it's a pretty good one on sort of policy relevant timescales. And so it's very important that there's two components there. You have a component which is due to the change and a component that's due to wherever you are, assuming you're not back in pre-industrial. And there are some constants here which we kind of know about. The important one to really focus on is this rate of adjustment to a constant forcing, i.e. how fast the system would continue to warm if we were to stabilize concentrations. And it's about 0.3% per year, 3% per decade. So in other words, if you were to stabilize concentrations at 1.5 degrees, we'd expect about half a degree of warming over the next century, if you just sort of multiply. So that's that residual warming we're talking about. And that rate will prove really important. So just remember 0.3% per year. If we want to ask how forcing responds to CO2 emissions, again on decade to century timescales, it's a very similar expression. This is the change in the amount of atmospheric loading of CO2, the amount of carbon dioxide in the atmosphere, which is proportional to the total emissions over that period, obviously enough, yeah? But it's now minus something which is proportional to cumulative emissions to date. So we put a whole lot of CO2 in the atmosphere. If we then stop putting CO2 into the atmosphere, if you recall the picture, it starts to go down again. Yeah, so if delta G, I'm not putting any more in, is zero, then I start to see CO2 concentrations decline. So that's this is a constant, which Pierre knows the answer, and Pierre knows what it is. Okay, so now I just add some more constants, doesn't really matter, just the radiative efficacy, the gradient of the absolute global warming potential, all things that you're very familiar with, transient climate response to emissions, okay, and we put these things together, we see the cumulative CO2 emissions over a multi-decade time period is proportional to the so just flicking on through this. So the top one shows you the relationship between the cumulative CO2 emissions over a multi-decade time period and the forcing caused by that CO2. And the bottom one shows you the temperature, how that relates to the forcing, the temperature change due to those CO2 emissions, how that relates to the forcing. Now notice on the right, they're very similar. In fact, there's only one tiny difference. So those two constants, one is rho E, one is rho F. Okay, so if I subtract these, if I just subtract these two equations, I get this. Okay, the change in temperature. Because I've left myself too little time, I'm not going to talk about the non-CO2 components over there. So ignore that. It's very important. Mostly methane, but let's ignore it. Okay, so but this carbon dioxide-induced warming, okay, is proportional to the change in cumulative emissions, i.e. the total emissions over that period, plus a term that's proportional to this rate of adjustment to zero emissions, which is the difference between these two constants, okay? And they're both about 0.3% per year, so the difference between them is basically zero. So we tend to forget about it. But it's really important because it's the balance between these two big processes that gives net zero its force, that actually sort of tells us that net zero is what it takes to stop global warming. And there's a really important term in here, and I really encourage you to sort of think, because this will be a big issue, I think, I predict, I hope, over the next 10 years or so, as we try and fold this into climate negotiations. This is the rate of active removal that is required to halt warming to reach net zero, to reach net zero if the passive sinks fail. Okay, so if Guyana, Suriname, and Bhutan don't protect their passive sinks, okay, if we cut down all the trees, then that's the amount by which we would have to actively remove carbon from the atmosphere in order to get the result that we were promising to begin with. Okay, and also we mess up the oceans and do various other evil things. So we very much hope that doesn't happen, but so this is a hypothetical number, but it's a really important number because it tells you the amount by which we have committed the world to take carbon out of the atmosphere in the future, even after we've reached net zero. So when Europe says we're committed to climate neutrality, we tend to think, okay, we're going to get to net zero ourselves. But that means we're also assuming that nature will be doing this for us, okay? And we haven't, I think, collectively thought about how we make sure that happens and how we adequately compensate for the countries that are actually looking after nature. And I'm conscious that it's probably well over 5 minutes. Okay, so just to cut to a number, so if you want to make sure that your historical emissions no longer cause warming after your ongoing emissions are reduced to net zero in the IPCC assessment report sense, meaning active removals balancing ongoing emissions, then you've got to do either one of two things. You either have to remove 0.3% per year of your entire cumulative historical emissions in order to draw down concentrations in the atmosphere, or you need to protect passive sinks equivalent to half that amount. Why is it half? Because that's the perturbation airborne fraction that Pierre will explain to you. Okay, basically removing carbon from the atmosphere is half as effective as protecting a passive sink in terms of tons of carbon. Now for the UK, just to give you a number here, for the UK, that means either active removal of 240 million tons of CO2 per year, or protecting 120 million tons of carbon dioxide per year of passive sinks after 2050. Now that first number is similar to the UK's, is getting on 2/3 or more than the UK's current emissions. So that's a lot. And the UK's land area is probably not enough, and certainly because we're kind of budgeting on passive sinks, that they're all there in our carbon budget assessment. We're using every scrap of land we can to do active CDR. So we're just counting on the rest of the world. Maybe we'll be counting on Europe to maintain a passive sink for us or Ireland even. perhaps we need a conversation about, countries that have contributed a lot to historical emissions, but don't have much land or insufficient oceans to provide the passive sink. UK, Singapore, you can think of lots of countries that would be in this category. And so at the moment, rather than pretending that passive sinks can offset the impact of ongoing emissions, which they can't, we need a mechanism to support sink protection, which reflects the contributions that entities, companies and countries have made to the need for passive sinks. That seems to be fair. But that mechanism does not exist. But we can make it exist. There we are. Apologies for running over.
Here? Yes, thank you. It has been a while since I dealt with this kind of equations on physics. But yeah, probably that's why there is always a summary for policymakers as well. But yeah, I'm sure that there are other colleagues in the room who have followed well and might have some questions or some remarks later on. But what is important, I think, is that we see that the definition used and the accounting methodology used can really hugely interfere in what we report and what the atmosphere sees in the end. I would propose that we listen to the next presentation from Steve Smith, which is one of the lead authors on the state of the CDR report, and that maybe after these two presentations we can have a couple of questions for clarification, and then we move to the panel. You have the floor, sir.
Be interested to see who I disappoint and who I please by saying that I've just got a bunch of bar charts and pictures. Don't have any equations in this one. But I'm, like Miles, I'm at the University of Oxford, so we're close colleagues. I'm involved in the Net Zero initiative with him and a project called CORE, focused on the net part of Net Zero, the carbon removal side of things, or greenhouse gas removal, as we like to call them in the UK, leaving open the possibility of removing other greenhouse gases like methane and nitrous oxide. I didn't put my sort of logos down here because I'm going to focus on some work from the State of Carbon Dioxide Removal Report, which was really a collaboration that grew out of CORE and Oxford Net Zero and a bunch of other researchers around the world, really. Several research projects in parts of Europe and also in the US. We kind of got ourselves together about 2 or 3 years ago when these projects were getting up and running, and thought, wouldn't it be good to collaborate on something where we try to set out what we know? Because amazingly, there are some really basic questions about carbon dioxide removal that we realized hadn't been answered or documented, like how much is going on and how much might we need. So rather than put everybody's logos down here, for about the 50 or so authors we had contributing to this second edition, I thought I'd just put a link to the website and a hashtag if you want to dig in more and talk you through some of the key findings, what we found. And I wanted to start off with the definition because Miles has very helpfully really emphasized this point about active and passive sinks and the fact that planet Earth is helping us enormously, and we're banking on it continuing to help us by taking up through the land and oceans an awful lot of the CO2 that we dump in there in the atmosphere. But there's a lot of definitional uncertainty and confusion that goes on around. I even noticed in the earlier session we had this morning, carbon capture and storage was used sometimes a bit interchangeably with carbon dioxide removal. There are 3 really important aspects to carbon dioxide removal that I'd love you to have in your mind and be clear about. One is about where the CO2 is coming from. So when we're talking about removal, at least in the definition that we adopt that's aligned to the IPCC assessment reports, we're talking about CO2 coming from the atmosphere. So it's a flux out of the atmosphere. That's super important because that's what generates the removal of the negative emissions, which has the potential to maybe counterbalance residual emissions in a net zero context. We're also talking about durable storage. Now, there's differences of opinion on what counts as truly durable, but if you capture CO2 from the atmosphere, if you've got a wonderful shiny direct air capture machine, you convert that into a fuel, you combust the fuel, the CO2 ends up back in the atmosphere. That's not durable storage. And the third thing is this point about it needs to be a direct consequence of human activity. So we're not talking about the passive sinks that are helping us out already, but we're talking about a direct intervention. So 3 factors: CO2 comes from the atmosphere, is durably stored away from the atmosphere, and is a direct consequence of human activity. And if you apply that definition and look at the ways of doing it, actually, there's a really wide diversity of methods. We looked at 15 different methods, and these are methods which have at least some kind of reasonable grounding in the literature and are actually being at least piloted, so sort of exist to some degree. Now, a lot of these are at very early stages, so they're not really mature technologies. They're certainly not as far along the technology development curve as, let's say, wind power or solar power in most cases, although some of them are. So we sort of developed this fancy graphic to try and get people to wrap their heads around it. And you can see the list. You can probably find your favorite ones, but we're talking about a whole range of things which include afforestation and reforestation and forest management. This is where we are deliberately adding to the natural sink. Also, you can take the products of land management, you can put it into durable wood products. So where I'm from at University of Oxford, we have buildings with wood in them that have been standing for about 1,000 years. That can be pretty durable. Or you can create products such as biochar, plow that back into soils, or use it for other applications. People are, of course, using biomass for energy, and if you capture biogenic carbon generated and store that geologically, that can be a carbon removal. You can also look at other things such as mineralizing carbon in cement and concrete, and people are looking at actively speeding up the process of doing that as a carbon removal method, so you end up with mineralized CO2. People are looking at direct air carbon capture and storage. You can see that further down, and you're probably aware of the ClimateWorks CarbFix project in Iceland. Very exciting, got a bit of media headlines. That's the kind of that is the largest scale DAX project we currently have. People are looking at ways of intervening in the oceans as well. So there's a broad range, and there are real menageries. So this color coding is just to kind of highlight some of the key differences in technology readiness. So the things that are darkest colors already happen at scale. We plant a lot of trees around the world. Sadly, not enough to offset the fact that we're chopping down a lot of trees around the world, but that's a pretty well-established practice. And we build with wood at scale in a lot of places. But when you go down this list, you see there are things which are a much earlier stage of technology development. They have different amounts by which they could technically contribute to solving the climate problem. That's their mitigation potential. And the durability of storage is really important. Miles talked about durable net zero. If we want something that stabilizes temperature over decadal to centennial timescales, in particular, if we're still putting any fossil CO2 into the atmosphere, we need something that's pretty darn durable as a proper counterbalance to that. And that durability is actually really tied to where the carbon ends up in Earth's carbon cycle. So these acronyms in the carbon storage pool, you'll actually see when you start looking at storing carbon in geological formations or in minerals, that's where you get the kind of super durable carbon storage. So there's a really wide range of ways to do this. And how much is happening at the moment? Well, as I said, this was something we set out to answer, and we arrived at an answer, which we're sort of finessing over time. But the headline is that actually currently, so this is actually in 2023, essentially, through direct human interventions, we are removing about 2 billion tons, just over 2 billion tons of carbon dioxide from the atmosphere annually. That might be a larger amount than you're expecting. It's still an awful lot smaller than the about 40 billion tons of CO2 that we're dumping into the atmosphere, so we're a long way from net zero. And actually, the vast majority of this is through what I've labeled conventional CDR. It's essentially reforestation and afforestation projects in different parts of the world, including in Europe. And if you just sum up what countries are reporting in their land sector, you actually get a much bigger number. I think you showed it was that passive shaded region, and it's something like 6.5 billion tons at the moment. But as Miles explained, that includes a big chunk of what's happening as a sort of indirect result, the passive sink being enhanced through environmental change. So a lot of legwork has gone into sort of making an estimate which tries to trim that out and isolates the direct component, and that's this 2 billion tons. So if you take a magnifying glass and just look at a tiny sliver around the zero, this is the stuff which we call more novel methods. And that's actually 3 orders of magnitude smaller, about 0.1% of the total. It's just over 1 million tons of CO2 removal per year from what we can measure. What's that coming from? Well, on the right, the kind of mucky orange bar, that's biochar. So that's pyrolyzing biogenic material, and most of the time plowing it into soils. And this is happening in a range of very small-scale projects around the world, in the US, Asia, Africa, Europe, South America. And it tends to be small-scale projects, the photo on the left illustrating it, and happening in Latin America. Not always even done for direct climate purposes, because this is done as a soil amendment, so it can improve soil condition and crop productivity and so on. And that's making up about 2/3 of carbon, the novel carbon removal that's going on right now. The second slice is bioenergy with carbon capture and storage, and essentially all of this is coming from one plant in the US, in Illinois, which is producing bioethanol from corn, but is capturing a part of the biogenic CO2 from that ethanol production, and is geologically sequestering that. Then when we get to the really, really tiny slivers, the darker brown, that's enhanced rock weathering. And actually this is happening, so this is crushing up certain kinds of minerals like basalts and spreading them on agricultural soils. Again, if you do it well, you get an agricultural benefit. But those minerals actually soak up CO2 in the presence of water when you grind them up finely enough. And this is a really interesting one, because as far as we can tell, there are just a handful of locations where companies are actually doing this. These are CDR startups. The UK, Canada, Australia, and India. India is a really interesting place for doing enhanced rock weathering. But as you can see, we're getting down to the kiloton scale now, so sort of 6 orders of magnitude below the billion tons that afforestation and fossil fuel activity is at the moment. And actually, sorry, I mentioned Climateworks and DAX, which is probably the one you're thinking, where does that fit in? That's a fraction of the tiny slice right at the bottom. So that's happening, that exists, but it's, that gives you an idea of the scale we're talking about at the moment. How much might we need? So this is just to pick up on something that was a topic of discussion in the earlier session, actually. And I think during the panel discussion, we were talking about sort of right-sizing carbon removal and not overselling it, and what is its role? Well, if you look through the scenarios that are analyzed in IPCC AR6, for instance, there are about 550 scenarios in total that you could argue are sort of Paris relevant. So they group them into these C1, C2, C3 scenarios, which are basically buckets for how much warming do you get with what probability. C1 being the most ambitious, 50-50 chance of staying close to 1.5 degrees, going up to C3, which is sort of the 66% chance of staying below 2 degrees category. So depending on your interpretation of the temperature goal of the Paris Agreement, you might want to look at these kind of buckets. And we did a bit of work to sort of peel out, well, across the range of these scenarios, what happens? And of course, out to 2050, the big story is reducing emissions. That's this bar on the left. And the uncertainty ranges you see there are the 25 to 75% range. So there are scenarios out there, but this sort of gives you the middle of the range across the set. And we're talking about reducing emissions if they're currently, so this is gigatons of CO2 equivalent. So currently we're about 50 billion tons of CO2 equivalent in global warming potential terms. So we're talking about getting well below 30 billion tons of emissions reduction. And that shows you that CDR is smaller, but that has really strong option value in these pathways, because the models are generally, if they have the opportunity to do carbon removal, that is how they're getting to net zero on this timescale of sort of 2050. Now, just to come back to the definitional point, we talked about carbon capture and storage and CCS. So the infrastructure that you would use to transport and store carbon is really helpful for carbon removal, because if you have BECCS and DACs, you're using that infrastructure. But of course, that infrastructure may also have a use for fossil fuels. And that counts as an emissions reduction. That's not a removal because you're not taking the CO2 from the atmosphere, if you remember those three important features of CDR. So there's a few gigatons in many of these scenarios of fossil CCS that's in that emissions reduction bar. That's not counted as a removal. The removal is all the stuff where you're actually taking stuff out of the atmosphere, mainly in these scenarios through BECCS and land, but they're increasingly looking at DACs and one or two other methods. So the total amount of CDR scale up in these pathways, and this is scale up, so you've got to add the current kind of level of about 2 billion tons onto these. But it means that in total, we're talking about 7 to 9 billion tons of carbon removal in the 25 to 75% range across these scenarios by 2050. And if you look at the breakdown between novel and conventional CDR, it's kind of similar amounts. Now, there's been quite a lively discussion about, well, what's the sensible amount of carbon dioxide removal to aim for? And one of the pieces of work we did in the state of CDR was actually to try and address this question of sustainability, because there's been quite a few bits of research which have suggested that maybe the level of carbon removal and the level of biomass use more generally in these pathways is actually unsustainable. This is actually really hard work to do with the scenarios. But hats off to some colleagues in EIEEE and in Japan who actually applied some filters to these pathways to look at the amount of land, the amount of water used, some metrics to try and assess what might happen in terms of ensuring people all have access to the food they need around the world and the access to the energy they need around the world, and applied some biodiversity metrics. So looking at a more holistic sort of sustainable development goal approach to these pathways. And if you kind of pull out the subset which meet these kind of thresholds we set for broader sustainable development goals, you get this kind of picture. The kind of blue lines that what I've called a sustainable subset here. So we see even more rapid emissions reductions if you're serious about these goals. We see total CDRs actually about similar. So you would still be aiming for the same amount of total carbon dioxide removal by 2050 globally, but the mix shifts a little bit. We see a focus on more conventional CDR. This is essentially because you're looking to preserve more or enhance more ecosystems and restore them, and you get wider agricultural benefits, biodiversity benefits, water benefits, and so on, if done well. So I think that's quite an interesting message, but a sort of tentative message that's emerging. I really think more work should be done on this. I mean, the caveat, I've got a couple of caveats about this, really. One is that the database of scenarios as looked at by the IPCC is really not optimized to try and explore the true solution space around sustainable development goals. They tend to be focused on energy access and carbon. They do have sustainability criteria laid over them, but I think it's a real big shift to try and look at all these things holistically. So this is a start, but I would argue this doesn't include the full solution space. And actually a lot of these models are quite technology poor, in particular with regard to removals. So as I said, they tend to have BECCS, and it tends to be a very specific version of BECCS, you know, for electricity. They tend to have afforestation. A few of them are now including direct air capture and enhanced rock weathering. Very few have biochar in, or some of the other methods I mentioned. And the other thing is these are pretty kind of coarse metrics to overlay. So there's more work to do, I think, to drill down into these scenarios and have a more fine-grained analysis. But, you know, scenario sets are scenario sets, and you can point to numbers and whiskers, but sometimes it's important to pull out individual scenarios to actually intuit what's going on and tell a story. So in the state of CDR, we focused on 3 scenarios deliberately to try and pick out some of the issues and trade-offs. All ones which are in this C1 set, so give you reasonable odds of staying close to 1.5 degrees. So they're pretty ambitious scenarios with this amount of emissions reduction baked in that you can see in the big blue line on the left. But we looked at one which had more novel CDR, so with a focus on scaling up some of the CDR technologies. One with a focus on conventional CDR, so more land restoration, afforestation, reforestation. And we specifically looked at a no novel CDR scenario where there are no carbon removal technologies in there. And that's really quite an extreme scenario in the subset if you look at the emissions reductions that entails. But we thought it was important to look at that and say, well, if you're not going to scale up any of these carbon removal technologies, what does that imply? And one of the things we did with those 3 focus scenarios is said, well, so where are we headed, and are we on track maybe to reach those? So different bar chart here. I've moved the current levels of CDR onto the left, that 2 gigatons in the dark grey bar. And then I've plotted in orange the 3 focus scenarios and where they get to in terms of scaling up carbon removal in the years 2030. That's relevant for a sort of NDC timescale, and 2050 relevant for a long-term low emissions scenario and a lot of net zero targets. And you can see the scale up, and behind that we've overlaid our assessment of what we think countries are pledging to do through the UNFCCC process. So we looked at the NDCs to get that grey bar in 2030, and we looked at long-term low emissions scenarios to get the grey bar in 2050. This is actually, again, really hard because one of our messages is there's not very much transparency at all in the NDCs, and even less in the low emissions strategies. And of course, not every country has published a low emissions strategy. Interestingly, if you look at the NDCs as well, there are 1 or 2 mentions of novel CDR technologies starting to appear, but not really anything we can feel comfortable to quantify. So all of this scale up in the grey bar for 2030 is actually just through habitat restoration and afforestation. We have no commitments to start scaling these removal technologies on the timescale of 2030. We see more of the novel stuff appearing in 2050, and we see some of a scale up. But again, this is incomplete because not every country has published one of these, and it's quite hard to pull out the data. And if you compare that to then these pathways from the IPCC, you see that maybe if we have a no novel scenario, so we really go low in 2050 in terms of our CDR requirement, we might be just about getting there if we believe the long-term low emissions scenarios, and if we do all the work on reducing emissions, of course, which I pointed to. So the argument is we have a bit of a gap. That's dependent on the choices we make and the path we follow. And that gap is only growing, of course, as we continue to fall behind on emissions reduction. I just wanted to close with a few thoughts because I wondered if for this audience it might be helpful just to think through, what might be the next steps in particular for research and development. And so these are very much my own personal thoughts, coloured by the state of CDR and also the conference we hosted in Oxford in June, the 3rd International Conference on Negative Emissions, where we had a really, really rewarding time and a bunch of people from across different disciplines all looking at greenhouse gas removal. So I've got kind of 5 ideas, and I'd love to hear people's thoughts on these in the discussion. The first thing is building and continuing to foster and grow this pipeline for innovation for new CDR methods. I showed that there are 15 that are sort of starting to emerge. One of the other things we've done in the core project is we've actually dished out grants, but very small ones, kind of up to £30,000 for a few months, to UK researchers who have ideas for new removal processes, just, things that are ideas in their head and need a bit of money to demonstrate at the benchtop scale or in the lab scale. And the diversity and quality of ideas that have come forward is really fascinating. We funded about 12. We could have funded many more. And it's really interesting to see the Bezos Earth Foundation has actually got in on the act and said, we're going to dish out pots of 30,000 for people who have removal ideas. So there's still a lot of scope for innovation, I think, to come up with new ways of doing carbon removal. The second thing is, and if I was to really kind of focus in on one, I think I'd have to, if it had to be one, I'd really go for this one. It's an international and long-term site network. So crucially, what we're trying to do with removals is take CO2 out the atmosphere and store it away. And that means we really need to know that the CO2 stays where we think it's going to stay. We really want to know what the background baseline is. So what's the passive sink? And that means getting in there early, before you've actually intervened to do the CDR bit. We really want to know the durability and the sustainability. The worst thing would be, doing CDR and screwing up the broader environmental system. We want to know that we can measure these things doing the MRV. So these field sites could be a test bed for new improved MRV. And one of the exciting things we've been doing in the UK is we've been partnering with 5 demonstration scale projects that are trying different removal methods on different patches of land. And we're starting to find that, the people growing perennial biomass crops, they can make biochar with the biochar people. And we're also looking at enhancing peatland restoration. And they're saying, well, actually, we could put biochar into peatlands and peatlands, when well maintained, are a pretty good carbon store. So this idea of co-deployment is starting to emerge in the UK as having interesting potential. But one country can't go it alone. And wouldn't it be great if we had a kind of internationally coordinated network, long-term network for actually trying these things? And even when you get into forestry and geological carbon storage, which are two areas that have been looked at for several decades, not just a few years, it's kind of surprising how few sites we have where we're taking really, really good measurements to validate our models. So this goes across the piece for all the places actually where you can store carbon in the carbon cycle. Improved systems modeling and life cycle analysis. It was great to see some of the results in the earlier session. I can see that they're really thinking long and hard about how BECCS and DACs and other things fit into the energy system. But as I said, certainly for IPCC assessments, we're at a fairly early stage and we're fairly technology poor actually in terms of representing these removal methods. When you get down to the kinds of models that countries are using to set their own net zero targets, they still don't have many of these carbon removal methods in. Now, some are at an early stage, so you could argue they're not ready to be included yet. But there are some which are being deployed on the ground where we're seeing activity in countries, and they're still not yet really being picked up very well in systems modeling. And when you do life cycle analysis to check, what's the best fit to the system and where are the emissions that pop up elsewhere in the system if you're doing these activities, we've got a paper coming out soon showing that life cycle analyses are all using different definitions of systems boundaries and functional units. So there's a bit of work to be done to bring consistency there. On the social science side of things, public perceptions is key. We did a bit of work on that in State of CDR, but we have a lack of data, especially outside of Europe, on what people think about carbon removals. And again, when you start actually doing these things in field sites and in demonstration projects in real locations, you start getting a really rich picture of, who are the farmers who get excited by this stuff? What is it that people really like about these things and really don't like? And that can be quite different to some of the very conceptual conversations we've had before. And policy options are crucial as well, because the European Commission is thinking very actively about carbon removal certification framework. The US is going down the route of tax rebates through the 45Q. The UK is thinking about carbon contracts for difference. Sweden's doing reverse auctions for BECCS. So there's a really interesting sort of Cambrian explosion of different ways of approaching policy, and that's an exciting time to study that and follow those. The last one, data sharing, capability and training. Well, part of the logic of the State of CDR is to try and get that data sharing and capability. It was really nice that we had a question actually about skills earlier, and I underlined that for CDR as well. Suddenly a bunch of topics which were quite niche and frankly, not the most exciting topics for many people are becoming really valuable. So soil scientists and process chemists who actually understand how these different techniques fit within the carbon cycle are becoming really important. There's a real demand for those in governance in the private sector as well as in academia. And we haven't trained up terribly many of those in recent years. So I'll end there because I'm sure we want more time for discussion and questions. These are just the key messages from the State of CDR. You'll see I picked up on some of them, but there are other things around public perceptions and MRV that I'd be happy to talk to in more detail. But thank you very much.
Thank you for this very didactic overview of the report. Yeah, we learned that there is not only an ambition gap and an implementation gap, but also a CDR gap. Yeah, also thank you for making the link to sustainability, which we will also discuss with the next panelist. Yeah, and for proposing some topics and ideas for discussion. First, I wanted to ask from the organizers whether Alexandra is with us. Then I would invite also Soheil to take place, and then yeah, I guess we can start off with Alexandra. So yeah, so we had now quite some technical background and scientific background on what is CDR and where is it for, but there is a whole discussion on trade-offs. How do we use CDR in the short term, in the middle long term, and also in the long term, and how can we avoid also that the attention shifts from emission reductions to CDR as a solution, while yeah, it's clear also from the presentations that the potential is limited and that there also are many uncertainties and risks involved, and that it would be risky to do so. But on the other side, it is clear that there will be a need for CDR, and there will be a need for investment and for research into this. And so the challenge will be to strike the right balance. But I think we have Alexandra and Soheil with us to shed a light on this from that particular perspective. And then afterwards, I think we still have Mr. Martin, who will give a short presentation on Marine CDR, and also hopefully we have some time for some exchanges. Alexandra, you have the floor.
Thank you. Yes, so good morning from Cali, where I'm at the, can you hear me well? Yes? Okay, yes, so good morning, everyone. Thank you so much for the invitation. And so I'm in Cali for the COP16 Biodiversity COP. And so I was very interested in hearing also what Miles was saying about the importance of protecting the passive sinks. I think there's, of course, a lot of talk about how to finance this here, but having been in the climate and biodiversity negotiations yesterday, I say that there's still not a full understanding of the importance of protecting those passive sinks to get to net zero, and also of the sort of limits of removals. So yeah, so thanks so much also to Steve. We've had discussions about this before, and I think I really appreciate that the second state of CDR really integrates these sustainability elements. I do have to say that I wish that they weren't in chapter 8, but rather upfront, because I think based on the research we've done in a paper published in Science earlier this year on the sustainability limits of CDR that really looked more closely at the more recent literature that foregrounds this issue, I would say that this is a really important framing. I mean, the fact that there is a limited amount of sustainable CDR, in my view, should be really a framing element for the CDR discussion, because bringing it up front really emphasizes, as you did, Steve, and your team did in the state of CDR, that the more sustainable pathways to net zero are the ones that use the less CDR. And hence, really thinking of CDR as this like limited, scarce resource, at least the sustainable part, I think would be super helpful to sort of re-emphasize even more strongly that we need, the key priority is, as we all know, steep emission cuts. So I also wanted to mention that I will have to leave in about 20 minutes because I have to get early at the venue. It's the high levels segment today with the heads of states coming, but I just wanted to share, if I have like 2-3 minutes, a few of our insights from the paper. So yes, so basically our assessment, as I mentioned, was based on looking in depth at a relatively small amount of literature, as we found, that really, when talks about sustainability in CDR, really foregrounds that and takes, I guess, the most ambitious view of the fact that we need to address, obviously, the climate and biodiversity crisis together, and being really concerned up front with sort of the food security implications of large land-based CDR. So basically what we found in terms of this like small assessment that we think should be sort of taken up again as a priority in AR7 in the IPCC next assessment cycle, is that actually, so we did a sort of a range of where sustainability risk would come in terms of the amount of gigatons of CDR, and specifically looked at land-based CDR, so especially BECCS and afforestation, reforestation, and some other nature-based CDR. So what we found is basically that with BECCS, if you have a low carbon capture amount, level, then rates, I guess, sorry, that sort of sustainability risks could start to come in at the level of 0.7 gigatons of CO2 removed by BECCS. So that we've been talking about this need for like billion ton scale CDR. So of course that is quite low. And again, this we did in terms of an assessment looking at what the literature said and looking at basically what we think are unacceptable risks to biodiversity. So those come in a bit higher at 1.3 gigatons, but still, so all to say that it seems that perhaps this assessment we did took even stricter sort of sustainability measures than perhaps even your colleagues, Steve at IASA. But again, I think the whole point of this is that I think it's really our approaches with the state of CDR are complementary, because I understand you're starting from the assessment that there's a CDR gap. And I mean, that of course we need to scale up CDR, and I think we start from sort of the fact that we need to foreground these sustainability elements. And I guess also and in terms of afforestation, reforestation, what we found also is that low risk afforestation, reforestation would be up to approximately 1.3 gigatons. And with both of these figures, the way we did this is that we started off really looking at sort of a precautionary amount of land that could be deployed, could be dedicated, I guess, to these land-based CDR, considering all the other land uses and food security and the need to conserve biodiversity. So I guess from that, we also assess then like the scenarios in IPCC that are, yes, compatible with the Paris Agreement, and basically assessed, yes, to what an extent they overstep the sustainability limits that we found. And we actually found that, I have my numbers here, that so of the scenarios included in the IPCC AR6, the database with available BECS and AR data, which are not all, 72% and 29% of 1.5 pathways with high overshoot exceed our estimated BECS and AR risk levels. So, and then 82% and 39% of 1.5 pathways with limited overshoot overstep medium risk levels in 2050. I mean, these are just a couple of numbers, but again, it just, from all this analysis, the three basic conclusions that we drew in terms of recommendations for both science and policy going forward is that for AR7, we really think that it should be a priority to have a more strict and in-depth assessment of the environmental feasibility of the amount of CDR that's put in the scenarios, because this actually is not really assessed at the moment well. And for that, we also think that it would be super helpful to estimate sort of a sustainable CDR budget. That we looked only at land-based CDR, but we think that, I mean, sustainability issues, of course, are across all types of CDR, and in fact have probably, as we found, have been less assessed in terms of other types of CDR. So that would be our first recommendation. The second one is really, again, in terms of IPCC, to really, and goes back to your point, Steve, to really further identify what are the viable 1.5 pathways that actually do not overstep these limits, and that are hence compatible also with the Kunming-Montreal Global Biodiversity Framework that countries have also signed up to commit to protect biodiversity. And then again, to end, I guess, reframing the governance of CDR to really start with the fact that we have this limited amount of CDR, that hence we need to allocate it well, and goes to the point of the moderator, that we need to, make sure that today we're not using CDR to basically offset fossil fuel emissions, but are keeping it to the really hard to abate, counterbalancing those truly hard to abate emissions. And I think having this framing of sustainable CDR being limited really kind of refocuses on sort of the challenges of defining what are those truly residual emissions, and prioritizing it so that we can meet our goals. So I'll leave it at that. I hope I wasn't too long, and thanks again for having me.
Yes, thank you, Alexandra. And I should have said that Alexandra is with IDDRI, the International Institute for Sustainable Development and International Relations, and is currently in Bali and is following both the biodiversity and the climate change negotiations. Then I would propose, we are a bit over half time. give a similar time slot to
Yeah.
Soheil for an intervention, and then invite Mr. Martin as well in the panel for a short presentation, and hopefully we can then have also some interaction with the public, because you didn't have the opportunity yet to ask any questions or to share any views.
Yeah.
And Soheil is with
CMCC.
CMCC. Okay.
Yeah, I make it faster. So, yeah, great to be here. So I have just a couple of thoughts to share and not much time to take from you. I think the key points have been covered by the previous speakers, and we are in a very good set. We understand CDR, but I think about sustainability, we should also consider the fairness and equity. These are the two main dimensions also. If we think CDR is gonna be playing a major role in the future, then we should think from now, who will benefit from CDR in the future? Early movers, the companies, the startups that are starting now with novel CDR, let's say. We see that the geographical distribution are mainly in the global north, let's say. So are they gonna be the big players in the future where CDR is a basically major component of climate solutions? And then how are we gonna address the question of fairness in that world that we will live in, let's say, 20 years from now on? So that is one issue which touches on Smith when he was saying about this international cooperation, that we need to establish the networks from now on to make sure also about accountability of the CDR methods that are being deployed now. And MRV also is an important point that I want to touch on. We don't have very good understanding of how to measure the carbon which is taken up by these methods. And to connect it with yesterday's last session we had about the observations, I think there are very interesting developments happening in the observation side, from in situ to satellite imaging. How can we combine these and make sure that the CDR and carbons that are being claimed are verified and being accounted for correctly? So I think that is also important part. And the last point I want to mention is about the geopolitical situation around CDR. We see that the CDR options are not geographically agnostic. Some of them are ocean-based, some of them are land-based. Of course, there are novel ones that we talked about, like direct air capture or BECCS. Probably they can be deployed more or less in a wider range of countries and areas, but those who are very region-specific, then it will create by itself some kind of political tension, who will own this kind of technologies and who will develop them faster and more, if we will move again to the world that there will be some kind of financial system to fund this carbon that is being taken by CDR. So I just want to caution, especially policymakers, about that. A few weeks ago, we had a project meeting, one of the projects that we are involved with, Steve there, Uptake, and we had a stakeholder engagement with policymakers, and one of the issues which came up was basically this issue that we might have some countries who are moving in the direction that protecting these technologies, as you can see, for example, with electric vehicles in Europe and in the US, that we are seeing this kind of industrial policies and protection policies for keeping the supply chain within the geographical region. So are we gonna see something like that with CDR, or are we gonna move to a more open and transparent kind of sharing data and sharing technology? So these are a few points that I think it is important about the future sustainability of CDR if we think it is a serious option for climate policy. Yeah.
Okay, thank you very much for also opening this topic towards more the fairness and the equity dimension, and to situate this in the context also of the geopolitical context. Then I would now like to invite Mr. Martin for a short presentation. If you can please stick to around 10-15 minutes, then
Sure.
we would still have half an hour for interaction with the people in the room.
The brief is 10 minutes. I'll try and stick to it. So, hi, my name is Martin Johnson. I am currently co-director of a small consultancy called Ecodiversity, based in Southwest Ireland. We're working on various sort of projects on the technical side, also knowledge exchange and policy side with in Ireland and internationally on really anything that is aimed towards positive climate action. My background, I was previously an academic at the University of East Anglia in the School of Environmental Sciences in the UK, where I was a marine biogeochemist. I suppose I've been thinking about these issues for the past 10 or so years. Actually, I was looking back. We wrote a paper about evaluating some geoengineering options back in 2008. We've since rebranded geoengineering to carbon dioxide removal. If it's more socially acceptable, then that's good. So, sorry? We don't hang out with the SRM. Oh, yeah, right. Different crowd. All right, so the title of this talk is the title of a paper that we recently published. Thanks to Frank for the invitation to talk about this. You can read the title there. It arose from a working group set up by the Surface Ocean Lower Atmosphere Study, covering people with legal, economic, ocean science, carbon dioxide removal, and coastal science expertise. And to paraphrase one statement in the paper, safe and successful solutions will be scientifically sound, legal, regulated, economically viable, and just and equitable. So I suppose there are two ways to look at that. It could be suggesting that the onus is on the people coming up with the solutions to make sure that they are doing all of these things. But I suppose a more useful and constructive way to think about it is that the community needs to respond to this need for CDR to help facilitate people finding solutions by addressing the legal shortcomings, the economic or the financing shortcomings. I won't really talk about the just and equitable side of things in this talk, but it is obviously really important. But what I will talk about is 4 challenges that we face to make safe and successful marine carbon dioxide removal. You can see them there, I won't read them out. So we've seen this figure a few times already from Friedling-Stein et al. I've actually converted the numbers here to be in gigatons of CO2 or CO2 equivalents from the gigatons of carbon, because I think one thing that's really important, and one thing that we try to do in this paper, is look at, actually, let's get to grips with the scale of the problem and the scale of the solutions that there might be. We look at it in a slightly different way to year on year, actually, but we'll come to that in a minute. So why do we think the marine system is interesting and useful for CO2 removal? So just focusing on that, I think that the main thing is there's a huge blob there, which is the biggest non-geological carbon store in the whole of the carbon system, and that's the dissolved inorganic carbon stored in the ocean. Now, one of the complexities, but also one of the opportunities, is the complexity around the chemistry of carbon dioxide dissolving in the ocean. I won't touch on that now. I think it's beyond the scope of this talk. I would say I've kind of pitched this at people who don't really know anything about the marine system, so apologies to those of you who do. This is all going to be pretty simple stuff, I suppose. But there's a huge store of carbon in the ocean, or stock of carbon in the ocean. Also, the arrows, the natural cycle, those 296s in and out, are also very big numbers relative to the 50 or so of anthropogenic emissions. So if there are ways that we can twiddle the knobs on the system to make the down arrow a bit bigger than the up arrow, it doesn't need to be a big percentage change to have a big impact on the atmospheric CO2. And I suppose the complexity issue boils down to the fact that in the ocean, everything moves around. on the land surface, everything's kind of in one place. So if you're doing something in, in the field or in your back garden, that's where the carbon stays. Whereas if we do something in the coastal ocean, it potentially ends up in the deep ocean, and there are various issues around that. And just to highlight, I've also taken the liberty of putting Steve's number on here rather than the number in Friedlingstein et al. This number is slightly bigger, but it's still pretty tiny compared to all the other numbers there. Interesting to compare it with the budget imbalance, which is a number of orders of magnitude bigger. So we're not really scratching at the problem yet. So we've talked about additionality and durability a good bit, so I won't go over those again. Another important concept, which does apply to terrestrial CDR as well, but it's very important in the ocean, is the predictability. So can we be sure that we know what's going to happen down the line after we take an action or make an intervention? I think the main things to take from this figure, I won't really talk a great deal about classic blue carbon, which is salt marshes and mangroves and possibly wild seaweeds in the coastal ocean. But just to highlight the salt marsh there, salt marshes are systems that quite commonly accumulate carbon, but also release carbon to the atmosphere. So the system is complex in many ways, and there, the problem is that not all of the carbon that's accumulating or being released is coming from the atmosphere, because they're at the interface between the land and the ocean, and there's commonly flows of carbon through salt marshes coming from the terrestrial environment, some of which gets accumulated, some of which gets released, but also salt marshes are probably storing some atmospheric CO2 as well, so it's about net rather than gross emissions. And similarly, the coastal ocean, which is the bit of marine science that I've worked most actively in for the last 10 years, lots of it is commonly a source of CO2 to the atmosphere. So does that mean we can't do any useful CDR in it? Well, no, I would argue that reducing the emission, a natural source, is as effective as increasing a natural sink. So that's fine. And look, we go out, there's many complexities in this system. There's this continuum, I suppose, of from river to open ocean to deep ocean. And it's all interconnected through shelf seas. We have exchanges between sediment and water. We know that coastal sediments are huge carbon stocks. We don't know whether they store carbon. I think language is something that we need to be careful around here, and the concepts of a big pool of carbon that's not changing versus year-on-year storage or sequestration or whatever you want to call it. So we have a big stock, and there's interactions there in both carbon and nutrients, nutrients being the drivers of primary productivity in the ocean. We have microbial cycling throughout the ocean, so that's phytoplankton and bacteria and their interactions, and some of that sinks to the deep ocean. And yeah, I would say in terms of the natural system, we don't know how much of the carbon fixed in shelf seas ends up in the deep ocean, where it could be locked away in a number of different forms for 2,000 or even 50,000 years, depending on the form of carbon, and how much of it stays in the surface ocean and re-equilibrates with the atmosphere. So many uncertainties. Let's look at a simple intervention, and one that people are looking at quite actively at the moment. If we grow some seaweed in shelf seas, there's loads of nutrients coming down the rivers, so that's pretty useful. What we know it will do is reduce the CO2 efflux in the area where we're taking CO2 out of the surface waters and turning it into seaweed. What we don't know is what happens in these downstream effects. So how does it affect the interactions between sediment and water, or microbial cycling, or the air-sea CO2 exchange in the open ocean? I'm not calling out seaweed as being a bad idea here, by the way. I think it's probably one of the simplest forms of CDR in the marine system. It's like growing trees on land. You can measure how much carbon you've taken up, and these downstream effects of seaweed are probably minor unless we go crazy with our kind of quantities. So I'll try and go through this pretty quickly, but I think it's quite important. In the paper, we look at cumulative emissions and cumulative emissions gap and the cumulative impact of CDR, so that we can look at the impact through time. So this is the UNEP emissions gap report 2023 data turned into a calculation of cumulative emissions gap. So how much excess carbon is in the atmosphere through time If you look at the 1.5 degree worst and best case, you're in the middle there. By 2050, it's maybe 600 gigatons of CO2. 2030, we're looking at 100 or 150. So just a bit of a thought experiment. What's our ambition for carbon dioxide removal or marine carbon dioxide removal? And then let's say we can grow at some fixed year-on-year growth rate, 2030 to 2060. Then we can back calculate what we need to sort of bootstrap by 2030 to be able to do that total emission. So let's say we want to do 50 gigatons of CO2 by 2060, which is down at the bottom of that graph of the likely emissions gap. And maybe nuclear is a good model for year-on-year growth, 11%. It's high infrastructure, high regulation, which is probably where we need to be with a lot of CDR solutions. Then we need to be doing 0.2 gigatons per year by 2030. Equally, ignore the aeroplanes for now, 19% year-on-year might be a more optimistic. So let's take something like solar PV has grown 26% year-on-year the last 8 years. That's kind of distributed, and there's a huge demand side pull. So maybe 26 is over optimistic. Maybe we could do 19%. In that case, we need 0.04 gigatons, 40 megatons per year by 2030. Now, that's normal economics, right? This is a kind of war footing kind of situation. Maybe we can do something much bigger. And the American tank and airplane industry did 100% year-on-year for 4 years. At the end of that, they were running out of resources. Great. So just to say, maybe that's what we need. Now, maybe normal economics doesn't apply, but I think it's an interesting thought experiment. So if we need 0.04 and then we can grow at 19% a year, well, currently we're at 0.0013, and actually none of that's marine, but let's put that aside for now. If we double that every year for 5 years, as it happens, you get to a 0.04. So this is potentially within our grasp, but actually maybe we want to do more than 50 gigatons. Maybe we have to find a way of growing more quickly. So I suppose the challenge, the thing to highlight here is that scaling is an enormous challenge for CDR, whether it's marine or otherwise. So just looking at the marine side of things, so there's a list of CDR interventions on the right. Just to highlight, I've called these technical for the point of view of the talk. They've also called geochemical or sort of open ocean solutions. But these are ones where we're really intervening in the natural system in some way, whether we're changing upwelling of the ocean or adding stuff to the ocean. And then the others, aquaculture, I've pulled out separately. Aquaculture, growing seaweed using the excess nutrients that are coming down the rivers to take CO2 out of the atmosphere. And then our nature-based solutions, so maybe restricting trawling reduces CO2 release into the shelf seas. It's a big maybe, potentially at 0 effect. And then coastal restoration and coastal stop loss are our blue carbon actions. So stopping the loss is stop destroying what we have. And then restoration is aggressive restoration to pre-World War II values by 2050, and then ongoing storage year on year after that, which I'm not saying is realistic. It's just just for the scale of things. So, and then in the paper we present a minimum and a maximum. We call them minimum and maximum because they're based on the minimum and maximum realistic literature values for potential potential annual storage. And then we apply growth scenarios, which we can discuss in the lunch break, but we apply a series of growth scenarios. So we've had to call them minimum and maximum because we're working with literature values. Actually, I'd probably call them realistic to optimistic, and then wildly optimistic. But within the constraints of what's in the literature, this is where we are. But I think the important thing to note is that in either of these scenarios, before 2050, we're not likely to make a significant impact on the emissions gap with marine solutions. Later on, potentially significant. Just very quickly, I'd point you towards this report that's highlighted here by Liebing et al., which has a lot of interesting stuff about the legal situation. A lot of those technical solutions that I mentioned involve literally dumping stuff at sea, and that's explicitly illegal under international law. So if we want to do that, we're going to have to do something with legislation. And in 2013, there was an amendment to the London Protocol on dumping at sea. to say that marine geoengineering, so it hasn't caught up with the rebrand yet, is only allowable for scientific research, and that's yet to be ratified 11 years on. So international law isn't going to, be a good framework for this. Equally, economics, it seems like there's a bit of a gold rush on at the moment for CDR, marine or otherwise. And I won't talk about carbon markets. I think most people will know about it, and lots of people here have more expertise in that than I do, but they're not really going to work for this long-term action. We don't value durability or predictability of carbon stores, as I understand it. Or, do we need futures markets for carbon storage? Because if we have this scaling problem, the sooner we start, the more value we're going to get later. Those options that we think are a good idea and we invest in, and then they turn out to be damaging because of some unforeseen downstream effect, which is particularly likely in the marine environment. How do we identify those, incentivize people stopping doing them, and support the people who are losing out from it? And I suppose my concern with the economics is that policy is maybe moving slowly when the industry is moving fast. And the technology industry is all over this at the moment, and investors. So I think the fourth challenge, which I think is also the one that probably solves the others, is about governance. I don't really want to go through this in too much detail, but just to go back to what Jonathan was saying about the need for integrated systems thinking, I think we've touched on it in a number of the talks. At the moment, we're still siloed. We're less siloed than we used to be, but we need to be really interactive on these problems. I think this goes beyond Marine CDR and beyond CDR and through to emissions reduction and climate action, but somehow we need the forum that allows the connections, particularly between research and policy and business, but also the wider community in terms of making sure things are socially acceptable, that move at a decent rate to meet the problem, and bring people along with us. So I'll leave it there. Thanks very much. Thanks.
So thank you for laying out also the challenges related to marine CDR and for a reality check also in terms of what we can achieve by 2050. So I think now it's up to the room to intervene and to ask questions. The panelists are here. I think Alexandra, she might have left, maybe, I don't know. But yeah, the floor is open. I will take care of the mic cube. Yeah.
Many of these CDRs are converted into carbon credits that then are bought by companies that do offsetting. And it was mentioned in the first speaker that many of these offsets are not really, well, many of these carbon credits are not really offsets. Now, for me, there is an intimate connection between offsetting and insetting. Meaning that, as you know, companies first do the homework, do the insetting, and then do the offsetting. So the price of the internal carbon price should be tightly related to the price of a carbon credit. Now, the prices of different carbon credits for different CDRs vary enormously. You have from 5 to 10 euros to 200, 300 euros. But we know that for companies to really seriously do the insetting, the price of a carbon credit should be expensive. So I would like to know, your views on what type of solutions should be prioritized for companies to seriously do the insetting.
Yes, I would propose to take a couple of questions and then give the floor to the panel. Anyone else?
Just on the CDR report, you pointed out that there's a long way to go in terms of, have you got sort of horizons by which, I may have missed it, but Martin showed the horizons for delivery of Marine CDR, so to speak. Have you got the same for other novel? What strikes me is we're at a very low starting point. There's a whole sustainability issues, and then there is this sort of investment bandwagon out there, and how best to bring those together. Have you got thoughts on that?
Wait. Sorry. Is there another question? Another intervention? I will take 4, and then we give the floor to the panel. Sorry, it's a memory check.
Thank you very much. A quick question for Stephen and for Martin. Maybe Martin, in terms of small scalable prototype projects, is there anything on the horizon, any kind of sandbox projects that are worth keeping an eye on? And Steve, just in your, maybe it might be a silly question, but you mentioned one of the CDR techniques, biomass sinking. Is that what it sounds like it is? And maybe could you talk about some of those novel, those 30K projects, some of the ideas that people are bringing to the table that mightn't be in the literature at the moment? Thank you.
Hello, thank you. I think my question is also related to the presentation of the report, the CDR report, and Steve's presentation. My name is Zoltan, again, from DGRTD. And the question relates to the framing. I was very happy to see already in the first edition of the report the clear definition of what we consider as CDR, that it has to be actual removal from the atmosphere, it has to be stored, and it has to be durable, and all fine. But then in the list of examples, I heard some examples which don't necessarily provide that. For instance, the construction from wood or biochar, it can provide that, but these actions don't include the removal, because you are just moving carbon from a terrestrial pool to another terrestrial pool. And for it to lead to any removal, you have to make some strong assumptions about how it affects land use in the past or the future. And if it's in the past, like wooden construction from wood, which grew 100 years ago, how do we count it as removal that we need for the future? So my question here is that how do you see it in the framing, or I haven't read the new report fully, so I just looked at a summary and just heard your presentation. So I'm just wondering how it relates to the framing and how it should be handled in practice, because just shifting from ecosystems to an artificial pool is not necessarily giving us removals, the kinds of removals that we need for the future. Thank you.
Yes, thank you. So I think we have a question on the height of the carbon price and how to still give incentives for reductions, on the time and potential for CDR over time. And I think a question that I didn't get entirely on project types, I think. And then also on basically removals and risks from for moving from one pool to another. Maybe first, I think most of the questions were in the first place addressed to you, so maybe you could start and the other panelists could complement.
I'll have a go and tell me if I miss bits, and I'll also try not to be too long. But okay, so Frank, yes, we've got numbers for 2030 and 2050 in particular that I pulled out, but also we made all the underlying data in the report available, so you can pull out time series. We focused on CDR as a whole, and then did this kind of split between conventional and novel, so we don't get down to the level of individual technology levels. But I mean, I broadly agree with what Martin showed. I mean, Martin Uzone did on blue carbon, but I think the gap from the UNEP emissions report is similar sort of numbers for the sort of gap we look at. We didn't look at it in cumulative terms, but that's a nice way of looking at it. So we can dig out some more numbers for you. I do really like breaking it down a bit more to think about individual methods, though, and I hope that's the direction we increasingly go in. So with emissions reductions, we do still talk about the emissions reduction challenge, but we have way more sophisticated conversations in focused fora about home insulation, about wind power, about EVs, about solar cells. And I hope that's the way we're going with carbon removal, because I think a lot of these things are different. And so to pick up your question, yes, that there are a lot of people who are trying things. that are really quite unusual. So one of the projects, which was the largest novel CDR in terms of reported deliveries until fairly recently, was a project which actually takes agricultural wastes in the US Midwest, so kind of maize, corn stover, turns part of it into a biochar that they return to farmers and they apply it to their soils, but then actually takes a significant bio-oil, a liquid fraction, and injects bio-oil into a geological well rather than gaseous CO2. There are other people who are doing biomass sinking, and that is what you think. So there are people, actually, as a project, there's a company called Running Tide, which folded recently, but was exploring sinking biomass and other materials into the ocean. I'm not going to comment on whether any of these are good ideas. I mean, biomass is quite useful for lots of other things, but these projects are exploring and existing, and so we kind of feel it's important to track them. And I think for some of these newer ones, there are really interesting questions that you touched on, Soheil, about how do you measure what that's actually doing to the carbon cycle and whether it's doing what you want, as well as broader sustainability implications. And that leads me a little bit to the other question about insetting and financing, because a lot of these projects look really different. And when we talk about pricing, it's probably important to have a granular discussion about whether we're talking about an afforestation project or a direct air capture and storage project, for which there are 2 orders of magnitude difference in price. So we're starting to see price data emerge. And, you know, afforestation projects are more expensive than an average voluntary carbon offset project, but they're at about, $20 per ton, I think. DAX is up at 1,000 or sometimes more per ton. And you've got things in between like biochar and enhanced rock weathering projects. Now, some of those, I think, lend themselves to being slotted into supply chains, and therefore the insetting you were talking about, where you're not just buying a project which is completely separate from you and just taking the credit and not really learning much about it, but you're actually trying to work with your broader supply and value chains. And so I think some of these things like biochar and enhanced rock weathering, there are still some really important scientific questions to iron out, but they're things that actually are adjacent to existing agricultural processes a lot of the time, and so could actually be dropped into, broader agricultural supply chains, for instance. And there you're talking of prices, in the few $100 per ton, but they could come down. And you talked about them sort of how do we then align them to broader decarbonisation and issues with voluntary carbon markets. It is important to note, I can't remember the exact numbers, but I think it's something like 40,000 tons of these novel removals are being traded as credits. That's actually not the majority of them. So the BECCS projects to biochar, most of that's not turning up in carbon markets. So carbon markets are an important and interesting driver, but they're by no means the only one right now. There was another question, wasn't there? But maybe I'll hand over to other people.
Yeah, I'll try and answer that one. Where to start? Yeah, so in terms of marine projects that are of interest, I mean, there are a wide range of things going on. I suppose it's worth mentioning one of the ways that we get to that 2030 level to then grow is by having as broad a selection of pilot projects as possible, so that we can then, we have to choose the ones that are going to work and push those forward. So I suppose the marine ones that seem most feasible and with the biggest capacity that people are working on is growing seaweed and doing something with it. Now that might be sinking, or maybe biocharing is a better idea, but it is important that we do something that locks that carbon away permanently. And I'm not sure that's a message that's entirely landed with all of the seaweed community at the moment. People are often saying, "Oh, growing seaweed's great because it sequesters CO2," but then they're selling it to the pharmaceutical or the food industry or whatever. So I think ocean alkalinity enhancement, which is the marine equivalent of the enhanced rock weathering, which is kind of the same thing in many ways, has lots of interesting potential, particularly in terms of its scalability, because there are a few companies, and there are a few different methods, a few companies like Captura, which I'm sure you're aware of, who have a lot of seed investment funding at the moment, who basically have shipping container size systems with relatively simple plumbing and a proprietary bit of technology that allows them to pump seawater through and add alkalinity to the seawater one way or another. And the nice thing about that is that that's kind of a permanent change to the ocean until it comes out the other end, in subduction and in geological time. So that alkalinity enhancement is quite exciting. But there's all of there's the need for MRV, there's the complications around it has to remain in contact with the atmosphere for long enough to have an impact on the short term. If it goes into the deep ocean quickly, then we've got to wait 2,000 years for the benefits. So yeah, I think that the community is actually pretty good at picking up the things that are happening and documenting them. So I think we're quite up to date. I think there's I'm sure there's stuff very early stage, but I think we kind of know about the broad range of techniques that people are really thinking about at the moment. And so for marine, it comes down to, ocean alkalinity enhancement, seaweed, doing something with it. Obviously there's blue carbon, but it's very small scale.
And I've remembered the other question, sorry, yeah, about definition of CDR. Very quickly, you're quite right. If you're doing something like biochar or BECCS, the point where you're doing the flux out of the atmosphere is not when you're making the biochar or doing the energy. It's the fact that that biomass has taken some CO2 out of the atmosphere when it's grown, and then you are, for it to qualify as CDR, putting it into some kind of durable store. And so we're talking about the fluxes out of the atmosphere that result in some kind of durable store, but that's a point not everyone gets. There's a philosophical question. I think there are still some interesting questions around the edges of the CDR definition to work out. So the philosophical question I'm currently wrestling with is a lot of CO2, or it's kind of at the gigaton scale, I think, or at least the hundreds of millions of tons, is taken up naturally by the built environment from cement and concrete. So we emit a lot when we make it, and then that's slowly soaking up CO2, mineralizing as it's standing in a building. And that's accounted for in the global carbon budget, for instance, but we tend not to call that CDR. And if you kind of ask people why, it's because, well, we didn't really mean to do that, and we created an awful lot of emissions when we made the cement. If you do reforestation, you've kind of hollowed out a carbon sink and put the CO2 into the atmosphere, and then you're building it back up again. And often reforestation happens through the abandonment of agricultural land. So you're not really actively doing something other than moving away from the land. So is one CDR and the other not? And if so, why? I'm still working that out. If anyone has an answer, let me know.
Fascinating.
Maybe Miles has an answer.
Well, I was going to pick up on that because, I mean, come back to the insetting point, and I think with the proliferation of different methods of CDR, I think it's helpful to realize that we've actually got a much smaller number of long-term storage destinations for the CO2, and I think it's quite helpful to think of it in terms of less of the method than where the CO2 ends up, and also to associate. And again, this is a policy decision, but I think it's one which would be very helpful, would be to associate storage destinations with sources of CO2. So if you want to claim that you're offsetting or compensating for in some way the generation of CO2 from a geological source, it should go into a geological timescale sink. And I would, in the category of geological timescale sinks, storage sites, I would put clearly geological formations themselves, possibly ocean alkalinity enhancement, I mean, to be discussed.
Yeah.
And then the list kind of runs out. So that's a simplification in the sense that there's not very many places to put CO2 that actually compensate for generating it from burning a fossil fuel. And so I think if we get more of the policy community understanding the fact that effective compensation for burning a fossil fuel means putting the CO2 into a geological timescale storage, then I think it really addresses the whole insetting problem. I mean, if somebody comes up with a $50 a ton way of getting CO2 into geological timescale storage, I think we can all go home. We're good. But we're a long way off that at the moment. I mean, any method which results in CO2 ending up in geological timescale storage is multiple hundreds of dollars per ton, in some cases thousands of dollars a ton at the moment. So that changes the mindset on insetting, because clearly then it's like, okay, if that's what it's going to take, then we'll obviously this is not something to be undertaken lightly. Just on that point, though, I just wanted to pick up on something that Alexandra said, and it's perhaps a little unfair because she's probably already left, but I did want to question one we do need to emphasize the limits, possible even past 2050 non-existence of additional CDR capacity in the biosphere and at the Earth's surface. We don't know what's going to be happening to the biosphere after 2050, but it's possible that, you know, continuing to dump CO2 into the biosphere may in fact be impossible beyond that. So we should definitely acknowledge those limits. On geological destination CDR, I think we're so far off exploring the limits of that I think it's actually quite unhelpful at the moment to say, oh, let's keep this for the future and not use it to, for billionaires to compensate for their private jet flights and so on, because we need to scale it. And in every technology, we've typically seen it adopted to start with by the rich, so to speak, and then propagate down to everybody else. So the idea that we should keep reserve novel CDR because it's a scarce resource, I think is flawed. Well, at least there's an alternate view that we should encourage anybody to do it, no matter how frivolous they are, because we know we're going to need that in the future. We need it scaled up.
Yeah, so I wanted to touch on the scaling of the CDR. It's a very important issue. And I think it also touches on what Max in the earlier session was saying about the framing of the problem. So CDR, one of the early negative publicity that it got was from using it for enhanced oil recovery in the US mainly. And so it created huge backlash from mainly climate activists and climate scientists that this is not the purpose of removing to take more oil out of the ground. And I think now we have to focus on the co-benefits of CDR in the communities. For example, nature-based solutions are now becoming more important. And as we have heard from the adaptation community, these are very important tools in the adaptation toolbox. And they can count as some of the CDR options here. So similarly for ocean and other land-based CDR, I think we need to try to make a positive case for CDR beyond just removing carbon, but other co-benefits that it has for adaptation and solving other climate problems. So this helps for the scalability of the problem.
Okay, thank you. Yeah, if I may, I just want to add, it's important also to have some safeguards if you want to use this nature-based solution, because there might be more with risks than co-benefits at sometimes. Yeah. You would like to add
just
something
very
else?
quickly on Miles's point, I think there's the cost, but there's also the value. So, you know, there's great value in the geological stores, but then we also have a short-term problem. So if we can put carbon places where we know it's just going to stay for 100 years, at least we're smoothing out the really steep bit of the problem, but it's less valuable. So that the other side of the cost thing. And just on the trees going into buildings, that's CDR if it's new trees that are grown and then replaced with more trees, and we're storing it in buildings that would otherwise be made of concrete. But maybe old heritage buildings like natural carbon stocks could be protected on the basis of their carbon value, but it's going to be very small.
Yes, and there are still some philosophical questions remaining. Is there any other? I think we still have time for one or two. One, two.
Yeah, thanks a lot. Very interesting session. I personally learned a lot about the topic, but I would like to actually jump on the point made by Miles right now, because I mean, I have the impression, but I might be wrong, that the idea that CDR should be used for what is often called hard-to-abate sector is actually, let's put it like this, the right way to use it, or where we really need it. Let's put it like this. But then, of course, the question arises: what are hard-to-abate sectors? I mean, you put the idea of private jets out there. I think here in the room we would probably agree that these are considered not to be hard to abate. So not well, they're hard to abate, but is that really the necessity to do it? So yeah, just throwing out this question, do you have any views, or is there actually maybe a definition I'm not aware of, or is there a discussion about such a definition? What would be hard to abate sector, and where it would be most logical to actually use the limited resources of CDR that we have?
I would take the other question also, and then a last round.
Hi, my name is Angel Mead from the European Marine Board. We have a working group on looking at the monitoring, reporting, and verification of Marine CDR, so I really welcome the Martin's presentation. But one of the discussions that was there in this working group is also about related to governance and so on, is also liability, because many of these technologies on CDR, are provided by companies, so they sell that, okay, this CO2 will be, or this carbon will be stored for 100 years. But then the question is, who will make sure that this CO2 is stored there, and who's going to pay for potential leaks in the future and so on? So I don't know if there's any discussion currently going on, or you have any examples of who are thinking about that. Okay, will be the taxpayer basically paying for that, or because of course no company will probably exist for 100 years. So I just wanted to launch that question.
Thank you. Yeah, I would propose each of the panelists 1 minute for a quick response and for a final remarks, and then we will be on time to close.
There is a class of companies that typically do stick around for order 100 years, and they are companies that could be highly relevant to the whole CDR climate mitigation space, and they don't tend to get talked about enough, and I'm going to be talking about them this afternoon. I mean, of course, fossil fuel companies. But on the point of the private jets, I was being deliberately, I was picking something outrageous, and it worked because you were outraged. So, but if either we ban private jet flight, okay, or we absolutely require that if you're going to fly a private jet, you get rid of the CO2 permanently back underground. And it seems to me, therefore, the second option is very definitely preferable to just letting people carry on flying around in private jets, or pretending they're offsetting with planting some trees. So I think that's where, I also personally feel that the debate about, I actually think that for academics and policy people to sit around in rooms and discuss what's a hard to abate sector, I think is very dangerous, because that's, the people who work in the unlucky sectors that don't meet our criteria are going to have a view on that. And so I think the right approach is to say, well, we need to neutralize. Well, I'll get another chance at the microphone this afternoon, so I won't go on at that. But I'm sort of opposed to that kind of very centrally planned approach to CDR deployment.
Thank you very much for raising the question about kind of durability and what happens to carbon, because I think that's really key. And again, coming back to my point about diversity, it's different for different methods. So with geological storage, okay, you can do it badly and it might immediately leak out, especially around the wellhead. But if you do it well, you're pretty confident it's going to stay there, and it gets more stable over time, actually. Biochar, different. We know it's going to leak, but we know it's going to leak pretty deterministically, actually. So you can fit a curve to that. Okay, there are uncertainties, but you can kind of bank that as lost carbon, if that's not a mixed metaphor too far. And then trees, very different, not deterministic. It's wildfire risk, it's pest and disease risk. It's whether the person managing the land decides that actually they want to chop it down and build some houses. So I think they should be managed in different ways, actually. And I think what we should really do is seek to encourage people to maintain and enhance that store, especially where we're talking about non-deterministic risk, to actually incentivize people. So I would personally not really go for the things where you kind of bank on a certain loss assumption when the money is paid and then people get to wipe their hands and leave it. I'd want to encourage people to protect forests and protect enhanced forests and protect old growth forests. On the hard to abate thing, yes, there is quite a literature debating what we mean by hard to abate. I think that introduces a bit of a binary between people who are hard to bait or companies that are hard to bait and those aren't. No, sorry, I was looking because I was agreeing with you. No, I'm with you on this, Miles. I mean, we have a tool often for dealing with these things, and it's called economics. Like we work out what's more or less costly. I think there are other things we need to layer on, like scale-up rates, public preferences, environmental risks. But I actually just think transparency about how countries and organizations are planning to get net zero is key. And then we can have a discussion about whether we think they've got enough CDR, too much CDR, enough new techs on emission reduction, enough reliance on carbon markets. This points to issues that are much deeper than just carbon removal. But I think transparency is the key here.
So about the carbon credits, I think there are some ideas about temporary credits, and that might be something that, I mean, it has negative sides also, but that might be a solution. Also, there's a room for involving insurance companies on the credit markets to basically issue some insurance on certain markets that we are not sure about the durability. So I think insurance companies' role in CDR have been ignored, but I think they are going to be a major player in the field eventually. And about this hard to abate, my thought is probably the way to go around it would be to set different goals for abatement, mitigation, and CDR, not to get into these discussions. So we have a clear separate goal for removal, and we want to achieve that. And yes, of course, it will offset at some point some of the emissions, but we are not getting into this discussion. So we are just setting some target in terms of gigatons that we want to achieve by removals. Yeah. And then separately, we are reaching to close to zero, as we saw in the presentations, and in terms of conventional abatement options. Yeah.
I don't think I have much to add about which things are hard to abate, but on the on that kind of longer time scale, are our sinks, are our carbon stores secure? I think Steve's absolutely right. We need to look at different ones in different ways. So I didn't really get to talk about it in the talk because I was rushing through it, but predictability is something that's, I think, is really important in the marine system in particular. We have pretty good physical models of ocean circulation. We know if we add alkalinity here, I mean, well, we can predict with some certainty where it's going to end up, what the net effect is going to be. Or, the same could be for sort of biological CO2 drawdown out of the atmosphere. So I think maybe that comes back then to the value of the store, its durability, its predictability, et cetera, And I suppose the other thing, can't quite believe I'm going to say this, but hedge fund managers, for example, love a bit of uncertainty that they can speculate on. So is there a way to drive this system and just increase total CO2 drawdown by stimulating those kind of peripheral economic mechanisms that may or may not be a good idea for society, but people are going to start doing that kind of thing. So we need to know how long stuff is likely to stay for, but we also need to know how long it does stay for, so that the real value can be realized.
Since you mentioned hedge fund managers, I mean, that only works if there's a very clear downside risk to getting it wrong. So people have to then there has to be some liability if it does start to leak out again unexpectedly. Otherwise you end up in 2009 and everybody goes, oh well, and taxpayer picks up the bill.
Of course.
Okay.
Right.
Thank you. I think we got a good.
It's +1.
Yes. We got a good overview of where we stand with CDR and of the challenges that we are facing. I think this topic will be debated still a lot more over the coming years and the coming decades. But for today, I would like to thank the panelists and the public for the good questions and the good interaction. And you can continue this discussion over lunch, of course. Thank you, and a round of applause.
Thank you.